5.1c, Applications of Similarity. Um, 3 of these 4 questions are dealing with similar polygons. 1 is just working with a simple ratio and proportion. But this unit used to be a whole ratio, proportion, and similarity unit, and we kind of condensed it all. So that's why we get a lot of those ratio and proportion here within our similarity, but we don't separate it out and do an entire section on ratio and proportion anymore. But here we go. We got our problem here. It says a man looks into a mirror on the ground until he sees the top of a tree. If the man is 6 feet tall and the mirror is 10 feet away from the man and 47 feet away from the tree, how tall is the tree? Now, a lot of times you're just given this part down here, okay? The written part. Then you got to draw your own picture. Now, I got the picture drawn for you. You do not have to draw a man or a tree. The key parts to this are the 2 red triangles, okay? But again, we got this mirror on the ground, okay? And that's what the man is looking down into and then straight back up. Now we're assuming it's a flat ground, okay? And if we're doing that, what we can also assume here is that these are both right triangles, right? And because it's a flat ground, if I look down at this angle, it should bounce up at the same angle, okay? Now, these 2 triangles are similar, and we could prove that they're similar based on angle. Okay, we've got a right angle, and we've got this elevation angle that's going up to the person's eyes and up to the top of the tree, which should be equal. Excuse me. So we have 2 triangles and 2 similar triangles, which would be proportionate to one another. Okay, so I'm going to go ahead and label these different parts that we're given. It says the man is 6 feet tall, so this length, HF, would be 6. The mirror is 10 feet away from the man, so the mirror is right here, so MF, that length is 10. And the mirror is 10 feet away from the man and 47 feet away from the tree. So the mirror to the tree is 47 feet. How tall is the tree? I'm going to make that length my variable. Okay. Now, what I want to do here is set up a proportion, because I know that because they're similar, right, I know that the corresponding sides are proportionate to one another. Well, I'm going to figure out, let's do 2 sides that we know the distances that are corresponding, and we know their distances. We don't have a variable. So I'm going to go the smaller distance, mirror distance from the mirror to the person. I'm going to compare that ratio to the distance of the mirror to the tree, 47. So that's a ratio of these 2 sides, which they do correspond. That ratio should be the same as the height of the person to the height of the tree. I now have a proportion set up. 2 ratios that equal one another. I can solve by cross multiplying. 10 times x is 10x. 47 times 6. I would recommend using a calculator for some of these because probably can't do all of them in your head. Although I'm confident in my math skills, but I'm just being safe. 10x equals 282. To solve for x, I'm going to divide both sides by 10. I get 28.2. So how tall is the tree? 28.2 feet. Okay, we would want to write down the units in this case because it's asking specifically for a length, or in this case, how tall it is. Okay. Now this is one of the few days that I love taking the classes outside, and we just usually go right outside the door here onto the sidewalk, and I have a mirror that I pull out, and we measure how high somebody's eyes are off the ground before we actually go do this. But we set the mirror on the ground. We have the person walk from the mirror. They start slowly walking back, and they're trying to find the top of that cell tower in the mirror. Okay, and we are able to, through the measurement of their eyes to the ground, right, and the distance that they are from the mirror, we can measure that distance as well. We can go back in the classroom with those measurements. We can go back in the classroom and we can pinpoint where the mirror was on the ground. And using Google Maps, there's a feature that tells you how many feet away things are. Right? We can figure out how far away the mirror is from the base of the tower. And using those dimensions and what we just did here, we can determine how tall the tower is. Okay? So if we ever do come back, maybe we'll go out and do that. If we come back in face-to-face in January, maybe we'll go out. We'll play around with that a little bit. One thing we could also do is, because we do some right triangle applications, and I don't think we're going to get to those till second semester. Those use trigonometry, and we can also use trig with some of those outdoor problems. All right, so maybe we'll do a trig problem with the tower instead of a similar triangle problem. All right, moving on to our next example. So this one's a mirror problem. These are pretty common. You get some mirror problems like this with the similar triangles pretty often. Next one, shadow problems, okay? Same idea. I'm going to read this. You can use these two figures to solve the problem, but I'm going to redraw the two triangles over here so they're not overlapping one another. All right? So it says a lighthouse casts a 48-foot shadow along the ground. A 6-foot man standing next to the lighthouse casts a shadow that is 2.5 feet long. Based on this, find the height of the lighthouse. Okay, so I'm going to redraw this over here. So again, we got the sun. Okay, and the sun is obviously shining, and we got a tower. And that tower casts some kind of shadow. In this case, it's a lighthouse, but it casts a shadow. All right, I can make a triangle, a right triangle, right, with the shadow, the tower, or in this case, the lighthouse, and then the distance from the top of the lighthouse to where the shadow hits the ground. Okay, this will be our tower one. Now, the person's obviously going to be smaller. They're going to have a shadow, all right, and we can make a right triangle with theirs. Now, what happens here is because the sun is so far away, the angles that are being made here are going to end up being the same angle where the sunlight hits and the shadow is made. Okay, so these angles are all going to end up being congruent, which makes these two triangles similar. Okay, so let's see. Now the nice thing is these are all in the same units. They're all in feet. Okay, so let's fill in our blanks here. The lighthouse casts a 48-foot shadow, so this is the lighthouse shadow. The 6-foot man, so it's another 6-foot man, stands next to the lighthouse and casts a shadow of 2.5 feet. How tall is the lighthouse? Now, it's not always going to be how tall is something. You might end up doing one that says how far away is the shadow, how long is the shadow? You may do line of sight. You could say, what's the line of sight distance from the end of the shadow to the top of the lighthouse? Again, there's a lot of different ways to set this up, but that's why I like to draw the pictures so I can really identify the corresponding parts of the similar triangles when I set up my proportion. So I'm going to go ahead and do the same thing. I'm going to do shadow length of the man to shadow length of the lighthouse equals height of the man to height of the lighthouse. Okay. 2.5 times x is 2.5x. 48 times 6. 48 times 6 is 288. If I divide both sides by 2.5, get 115.2. Again, my final answer will be 1.5, 115.2 feet. Okay. All right. So these first two examples, definitely similar triangles, similar polygons here. In finding our answer, we use proportions to get that final answer by comparing the same types of things, the corresponding parts in ratios, and setting those equal to one another. Okay. This third example is one that it's not a similar polygon one. It's just a ratio and proportion one, and it's talking about exchange rates. So it says the current exchange rate from U.S. dollars to euro is 1 to 0.917. If you're planning to travel to Europe and are going to exchange $500, how many euros will you receive? All right. So what we're going to do is we're going to set up a proportion here, and the exchange rate is in U.S. dollars to euro. So I'm going to write that ratio as a fraction. So U.S. dollars to euros. Okay. So I'm going to write that ratio 1 to 0.917. Now, if I want to figure out how many euros I'm going to receive, I'm going to set up a similar ratio over here, but I'm going to make it the amount of US dollars I'm exchanging, and we'll make the number of euros I receive my variable. Okay. That way we're still staying, and if you look, this x value probably should be a little bit less than 500 because the 0.917 is smaller than 1. Okay, but let's go ahead and multiply this just to make sure. 1 times x is x. 0.917 times 500 is 458.5. So how many euros will we receive? Well, 458.5 euros. Okay. Now, for any of you that have traveled to Europe and have done the process of exchanging things, there's different rates at different places everywhere you go, and a lot of times there's fees assessed to them as well. So I think I went to Spain a few years ago, and I think the cheapest way for me to exchange my money was actually by using my credit card, because it was straight exchange rate with no fee. But I did want to get some cash because there were places that only accepted cash. So I did have to go exchange a little bit. And I think the cheapest place I found was at the airport. But lots of different places to do it. All right. Last one. So this one involves a scale model. Now, this is a three-dimensional. So you could say that this isn't a polygon that we are looking at, a similar polygon, but it kind of is, and I'm going to explain why. So it says a scale model of the Titanic is 107.5 inches long and 11.25 inches wide. If the Titanic was 882.75 feet long, how wide was it? It kind of is in this case. Well, the Titanic and its model are three-dimensional things, but in this case, we're only comparing the length and the width, which are two dimensions. Okay, so we could actually look at this as comparing two rectangles. Okay, so let's say I was looking above the actual Titanic. All right, hold on, I'm going to use some straight lines here so that I don't confuse everybody. All right, let's say I was looking above the Titanic. That'll work. All right, hey, not too bad. Now, so if I were looking from above, the Titanic would actually kind of fit into a rectangle that looks like this. Okay? Where the longer would be our length, and then the shorter side would be the width. Now, we know the length. They give us the length. It's 882.75 feet. 882.75 feet. Okay? We don't know the width. I'm going to make that my variable. I'm going to make that x. Okay, now, you know what? We'll just make it W. Keep it simple. All right. Now, we can do the same thing with our scale model. Now, the scale model is going to be a lot smaller, and I'm not going to draw it to scale, but my scale model will be the same thing. We got our smaller Titanic in here, a lot smaller, and it says it's 107.5 inches long, okay, and 11.25 inches wide, okay. Now, where we have to be careful here, all right, is if I'm going to compare similar side lengths, okay, corresponding sides, I got to be careful because inches and feet aren't the exact same conversion, okay? It's not like metric where we can say centimeters and meters because there's not 10 inches in a foot, okay? So what I need to do is I need to convert either these to inches, okay, the Titanic's length inches, or convert these two measurements of our scale to feet. Now, since I want my final answer in feet, I'm going to scale the inches into feet. I'm going to basically figure out what those conversions are. Okay, so I'm going to start with the width. If I want to figure out what 11.25 inches is in feet, basically I want to figure out what 11.25 inches is out of 12 because that's 1 foot. 12 inches is 1 foot. So I just need to do 11.25 divided by 12, and I get 0.9375. So 0.9375 feet. So that's how many feet 11.25 inches is, 0.9375. I'm going to do the same thing with the 107.5. I'm going to do 107.5 divided by 12, and I get 8. I'm going to go to 4 decimal places, 8.9583 feet. Okay. All right, so this is actually a pretty big scale model. This is probably something you'd see in like a museum. It's almost 9 feet long, so it's still pretty big. So let's see if we can figure out the actual length or the actual width of the Titanic using these two measurements. So I'm going to compare the length of my model, which is 8.9583, to the length of the Titanic, 882.75, equals the width of my model, 0.9375, to the width of the Titanic, which we don't know what it is. It's W. All right. Now, I'm not going to write all this down, but I know I'm going to cross multiply. So 8.9583W equals, and I'm going to do 882.75 times 0.9375. I get 827.578125. It ends up being a long number. But I'm going to take that big number, 827.578125, and divide it by that 8.9583, because it's 8.9583W. So divided by 8.9583, I get 92.381. We could actually probably round it to 2 places. We'll say 92.38. So my width, 92.38 feet. Okay.